Hi students, this is our second video for the topic of further functions for the International Baccalaureate course, Analysis and Approaches. In this lesson, we're going to look at how we graph the square of a function. So we'll start by looking at some of the features of the graph of the square of a function. The points with a y-coordinate of 0 or 1 will stay the same. 0 squared is 0, 1 squared is 1. We call these points invariant points. So x-intercepts are going to stay the same. The graph will always be positive above the y-axis. Vertical asymptotes will stay the same. Infinity squared is infinity. If f of x is in between 0 and 1, the graph will be closer to the x-axis. Now think about this. If f of x or y is equal to a half squared is a quarter. But if f of x is greater than 1 or less than negative 1, the graph will be further away from the x-axis. So here's our first example. On the same set of axes, graph the curves f of x is equal to x times x minus 2 and g of x is equal to the square of f of x. Now I've just done this on Desmos, let's talk it through. So the red curve is f of x. It's a parabola, it cuts at 0 and 2. Now when we graph the square of this, you can see, that's the blue curve, you can see it's always above the x-axis. We can see that the x-intercepts stay the same, okay, because 0 squared is 0. Anytime the y-coordinate was 1, it stays 1, because 1 squared is 1. Now, in between 0 and 1, the curve is closer to the x-axis than it was. So it's flatter. But when our y-coordinate was greater than 1, it's getting steeper here. Okay? Example 2. On the same set of axes, graph the curves f of x is equal to e to the x and g of x is equal to f of x all squared. Again, I've just done this on Desmos, but this example clearly shows what happens when y, or f of x, is in between 0 and 1 and when it's not. So the red curve there is e to the x and the blue curve is the square of that function. So you can see in between 0 and 1, when y is in between 0 and 1, the curve is going to be closer to the x-axis, but when it's greater than 1, it's actually going to be steeper or further away from the x-axis. And example 3, consider the function f of x is equal to x minus 2 all over 2x plus 1. Which points are invariant when g of x equals f of x all squared is graphed? So of course we want f of x to equal 0 or 1, and we're just going to solve those two equations. So firstly, when I put 0 in for f of x, x will equal 2. So the point 2, 0 is invariant. And when I solve 1 is equal to x minus 2 all over 2x plus 1, I end up with x is equal to negative 3. And so negative 3, 1 is also an invariant point. Which asymptote will stay the same? Well, that's the vertical asymptote, and we find that by solving 2x plus 1 equals 0. So x is equal to negative a half. What will be the equation of the other asymptote? Now, one way to do this is to find the limit as x approaches infinity of g of x. So I've just squared the top and squared the bottom. We can use L'Hopital's rule here, so differentiate top and bottom, and we'll need to do it again, and it's equal to a quarter. D, hence graph g of x is equal to f of x all squared. So on the right hand side, greater than 2, it's going to tend up towards that asymptote, like that. In between 0 and 2, it's going to be positive. So we're going to take the y value and we're going to square it. We'll end up with a positive number we can solve 0 is equal to x minus 2 on 2x plus 1 and find that there's going to be a y-intercept there. So it's going to end up like this. And then, gosh, this is going to be hard to draw. It comes through there. It cuts through that asymptote through y is equal to 2 and then heads off to infinity. On the left-hand side, it is, thank goodness, much easier to draw. When y is greater than 1, it is steeper, and when y is between 0 and 1, it is flatter. And so that's roughly what the graph looks like. I'm sorry about the terrible drawing, but you get the idea. You're probably wondering, is it possible to cut through an asymptote? And actually, yes it is. Because the asymptote is really about the behavior of the function as it tends towards infinity and negative infinity. And we'll finish off with a past exam question. The following diagram shows the graph of y equals f of x. The graph has a horizontal asymptote at y equals negative 1. The graph crosses the x-axis at x equals negative 1 and x equals 1, and the y-axis at y equals 2. On the following set of axes, sketch the graph of y equals f of x all squared plus 1, clearly showing any asymptotes with their equations and the coordinates of any local maxima or minima. So we're going to start by sketching y is equal to f of x all squared, and I'll just do that on this set of axes, and then on the new set of axes we'll translate the graph up 1. So remember, when we're graphing the square of a function, we're looking at the y coordinate and we're going to square it. So here it's 2, that's going to become 4. Any place where the y coordinate is 0 will stay the same, and anywhere where it's 1, it's going to stay the same. So this bit we know, it's going to come up through here, and then same on this side here. Okay, now this asymptote here, this is y is equal to negative 1. When I square that, I'm going to get y is equal to 1, which is a little bit weird. It's going to come through here. Now remember, in between 0 and 1, when we square it, we're going to get a smaller number, so this graph's going to come closer to the axis, like this. If I can draw it. This is a terrible graph. There we go. And then I've got to do this part here. It's going to be above the x-axis, obviously. It's also a fraction between 0 and 1, so it's going to be closer to the x-axis. So it's going to go around like this and then tend towards the asymptote. And again here, go around and like that. Okay, so that's roughly y is equal to f of x all squared. Now we just need to translate it all up 1. So our horizontal asymptote is going to be at y is equal to 2. And remember, we've got to label that. Our maximum point is going to come up here, so that's going to be the point 0, 5. These points here, where y was equal to 1, now y is equal to 2, so that's here and here. And these points where y was equal to 0 and now y is equal to 1. Okay, we're ready to draw this. Let's see how we go. It goes up like this and around like that. And then this turns around here and goes towards the asymptote, and the same on this side. And we've got minimum points here at negative 1, 1 and 1, 1. Okay, that's it for this lesson. In our next lesson, we're going to look at what happens when we graph the reciprocal of a function.